In 1989, asteroid 1982 was renamed 4116 Elachi in recognition of his service to planetary exploration. Dr. Elachi stepped down as director of JPL last summer to be succeeded by Michael Watkins, but he'll continue keeping his eyes on space. He's still on faculty in Caltech. Because now, as he will tell you, we're in the midst of a golden age of space exploration. It's an enormous endeavor. It inspires awe and wonder about our universe. It's an endeavor that shows America at its absolute best. Ladies and gentlemen, please welcome Dr. Charles Elachi.
Thank you, Terry. When Terry asked me to give this talk, he said, Charles, in addition to being informative, you have to be entertaining also. So I'm going to start with a joke, kind of related, to the heavens and what I'm going to be talking about. So recently, St. Peter convinced God to put an internet in the heaven and start using the internet. God was a little bit behind, the young people. So God sat down and said, okay, who do I send an email to? I'm going to send an email to the devil. So he typed an email and said, hi, this is God. How are things down there? And an email comes back within a few seconds saying, oh, it's great here. I'm sitting down, drinking my champagne. It's beautiful down here. So that annoyed God a little bit. So he sent an email back saying, how could it be? It's supposed to be hot, down there. Email comes back. He said, well, I found this JPL engineer who's a great mechanical engineer, and he put air conditioning, down here. So that annoyed God some more, and he sent him back an email, and he said, how could that be? All engineers from JPL are supposed to be in heaven. And sent him just now up here. And the devil sent an email back, said, no, I'm not going to send him to heaven. He's going to stay here. And God sent back an email. He said, you send him up now or I'll sue you. And the email comes back and say, and where are you going to find a lawyer? They are all down here. So I'm glad to see, I'm sure there are lots of lawyers in this room, but glad to see they have a good sense of humor, So let me start by telling you why I call this talk the Golden Age of Exploration. When I stepped down from JPL, they had a bunch of retirement event, and at one event, you all know Jim Cameron, from the animation, from the different movies. And he's a good friend of mine, so he came to one of the events, and he was speaking, and he said, when you think about it, the last 15 years have been really the golden age of exploration. So what I'm going to try to do today is to describe to you what has happened in the last 15 years, what we have learned, and what are the challenges for the next 15 years. Particularly earlier, I met with some of the students here who are high school students, so these will be the challenges that they will be, working on them in the next 15 years. But before I do that, I thought I would describe to you, why do we do space exploration? I get that question all the time of say, why do you do that? Why do you spend the money on doing space exploration? So the way I describe it in kind of a simple term is when you look up at the sky with a telescope, and if you take an area about the size of a dime, you put it at the end of your arm, that's about the area that is covered by this picture. And then you can see literally what look like hundreds and hundreds of galaxies. Each dot that you see in the background is like galaxy, like the one you see in a spiral. And each one of those galaxies literally have billions of stars, in it. And then if you zoom on some of them, that's what a little bit more detailed galaxy actually look like. And as you can see, there are literally, each one of them is full of these stars. And that's what happened in our galaxy, what's called the Milky Way. Our star is the sun, so it's like a little dot at the edge of one of these galaxies. And somehow, over the last 15 billion years or 14.5 billion years, planets formed around that star, which we call the sun. And this is our solar system. You see the 8 planets In actuality, depending on how you look at it, some people count Pluto as a planet, some people don't count it, as a planet. And you see our planet is that little blue one, the third from the left. And somehow, over the last 4 billion years of the evolution of our planet, we were fortunate. It had the right environment, it had the right chemistry, the right temperature, that it led to the formation of these cells. And these cells somehow got together and formed the beautiful life that we see around us. And what some of you might not know is that after 3.8 billion years, we got the Los Angeles World Fair Council. So the key question is, how did that happen? How did it start from those galaxies and the Big Bang? And here you and I are sitting down having this conversation. So what we are trying to do in our space exploration is to understand how did things evolve, how did the star form, how did galaxies form, how did planet form, how did life evolve, and how common it is. Because the chemistry and the physics is the same across the universe. So on one hand, you say life should be very common all over. That would be amazing. When you sit down and the first time you think, geez, there is life similar or different than us on another planet. And if we never find life, that would be equally amazing. Why did it happen only on this planet? And if there is life somewhere else, is it similar or is it different? Is it based on carbon chain, DNA, or is it something different? So this will give us a deep insight of how did we come about here. So what we are trying to do is what I call write a book about how did we start from a Big Bang and we ended where we are today. And of course, that's not going to happen by doing 1 or 2 missions. It's going to require maybe many generations to really understand how we came about and how we are here. So now what I'm going to do, I'm going to be showing you a series of videos. So the first one I'm going to show you is actually what happened in the last 15 years. So just, that little place which is called JPL, back in La Cañada, just from what JPL has done. So you're going to see a 5-minute video which show you what actually happened. So if we can get the first video, I think somebody back there. Yeah, here we go. fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in a twilight that knows neither victory nor defeat. And the team brought us victory.
I just wanted to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud. And this is the kind of thing that inspires kids across the country.
So that shows you what we have done in the last 15 years. And so it is really, truly a golden age. So now what I'm going to do is, I cannot cover all these missions, otherwise we stay all night here. So I'm going to pick a couple of them and give you a little bit of snapshot of what we have done with those missions. So the first one I'm going to talk about is a mission called Deep Impact. You saw a little segment of it there. And the belief is that a lot of the water on Earth came from comets impacting Earth because they are made of ice, but that's a theory. So what we wanted to do a few years ago is to send a spacecraft to encounter a comet and basically have a bullet, the bullet is 300 pound size, and have it impact the comet so we can see what comes out of it. Because the surface of a comet, is very, covered by a thin layer of very dark material, but what we want to see is inside of it, what's in there. And the challenge of that mission was not only to basically shoot at a comet and blow up a crater on it. That comet is moving at faster than the speed of a bullet, and our spacecraft is moving faster than a bullet. So it was like you try to shoot a bullet with another bullet, and you can imagine the technical challenges that we had to face. So the next video, I'm going to have you sit on the spacecraft that we were flying, on the bullet that we were shooting. We had a spacecraft, and then we shot a bullet out of it. And you'll see how we came and impacted, that comet. So if we can get the next. So that's a bullet that we let it go out. Now remember, the spacecraft is going at very high speed. And then we had an instrument on it which locked it on that comet so we can, zoom on it. And that's what we were seeing in real time, as the data was coming down, a few minutes after. And then basically we blew a big crater in that comet. And then we had the mother spacecraft analyzing what's coming out of that comet. And we did actually discover that the comet is made of water ice, H2O, like what you have in your glass in front of you, except frozen. And it has a lot of organic material on it. So one theory, we don't have absolute proof, but one theory is that life could have come from comets which came impacted Earth, both the water and some of the organic material, which after many billion years of evolution actually led to cells and so on. So that was one of the results that we got out of that mission. Now, people look at this video and say, God, it's easy, those guys at JPL, they are smart, but it's very easy to do these things. But in reality, it is rocket science, and every once in a while, things don't work exactly like we planned them. And the next video I'm going to show you in one case where we send a spacecraft went in interstellar space between us and the sun and collected samples from the solar wind because we wanted to know what the solar wind is made of. And the spacecraft was supposed to come back, and as it got in the Earth's atmosphere, to open a parachute and come softly on the ground. Unfortunately, what happened is what you'll see in the next video.
Sir, vector 200, put it on your nose, 8 miles, look for an
That's what happened when we started looking at this thing, and that capsule was coming all over. They said, where in the heck is the parachute? Why it didn't open? And then it crashed. Now, fortunately, at JPL, we built things so well that this one actually we still was able to get all the science from it, all the cells which collected the solar wind. But the point I wanted to make here is things don't always go perfect. Matter of fact, if we only wait until things work perfectly, that means we're not trying hard enough. I mean, when you do exploration, not only space exploration, but any exploration you do, there is always a risk because you are doing things for the first time. They have never been done before. And even if you analyze them and test them and so on, every once in a while something goes wrong. And the key challenge is how to make sure you minimize the impact, what we call to basically take risk but thoughtful risk. So we make sure. And that's one of the things that we teach our young people at JPL, that things cannot be perfect, even that we try. When you are exploring, always there will be setback, and particularly for the young people here. But the key challenge is not to be depressed after a setback, but to learn from it, find out what happened, and learn from it. And that's how we become better and better at doing things. So the next one that I want to, so let me move. I think I can control it now from here. So let me talk about Cassini. I'm going to take a little time and talk about it because you are going to hear a lot about it during the months of September. And I'll tell you in a minute why it's going to be all over the news in the months of September. Cassini is a mission, again, to give you a perspective a little bit. The first time we had a meeting about thinking about this mission, I was early 30s. And now I'm retired. So that gives you an idea how long it takes to plan these missions. So this was in the early 80s that we started thinking about it. And we formed a group which consisted of all these nations. And considering our world affairs here, we do almost all our mission have international collaboration, on those missions. So here we were collaborating with the European Space Agency and the Italian, Space Agency. And that mission was start being conceived in the early 80s. And then it was launched about 16 years ago. So it took a while, to convince Congress, get the money, design it, build it. And then it took 7 years to get to Saturn. And it had been now around Saturn for 12 years. So it's almost a lifetime. Now, that's good and bad. The bad thing is it takes you a lifetime to get your data. The good thing, you have job security. So once you start on those missions, they cannot let you go. You have to be around to do that. So Cassini was a mission which went to Saturn and has been in orbit around Saturn for 12 years. And basically, it's studying the Saturn itself, the rings of Saturn, and all the satellite, of Saturn. So I thought what I'm going to show you is just 4 days in the life of, Cassini. And I'm going to put you on the spacecraft. And what you are going to see, it might look like animation, but in reality, it's real data. So what you are going to be seeing. I think that's the next, yeah. So this is real images that you see in there. I mean, they look like artistically drawn, but it's real. That's what Saturn looks like. So to give you an idea, that circle at the top, that's about twice the size of Earth. So our planet would fit in a little hole, on the top of it. And Saturn is rotating, and you can see it has storms, which are on it, like huge hurricanes that we have here on Earth. You see the shadow, and these rings are very, very thin. So it's like almost, relatively speaking, paper thin. And they are made of a bunch of little rocks, which are made of ice and rocky material, which are spinning around Saturn. So we are sitting here watching the Saturn rotating. And look at that hurricane at the top. It's like a six-sided hexagon. How does that happen? We don't know. I mean, all the hurricanes we are familiar with are just circular, what you think of a hurricane. We are still puzzled about why does it have that shape, that for that hurricane on top of Saturn. Now, the reason I said it's going to be in the news is it's coming to the end of that mission. We're finishing the fuel on that spacecraft. So the way we are going to dispose of the spacecraft instead of leaving it as space debris is actually to bring it and crash into Saturn. So that's going to make news. It's on September 15. So the way we are going to crash it, we are going to get closer and closer and closer to Saturn to the point where actually we'll fly inside the rings. So we'll be crossing in between gaps of those rings. See there? Now, of course, that's risky because there might be little particles which are in there, but that's kind of the risk that is worth taking. So this is one of my favorite pictures, of Saturn. This was taken when Cassini was behind Saturn relative to the sun. So it was like here, I cannot see the people because the light is shining in my face, but if I put my hand this way now, I can start seeing people in there. So here, Saturn was blocking the sun, which allowed the spacecraft to take, images of very faint objects. And you see, I'm not sure you can see it very well, at the bottom right, that's us, Earth, as viewed from Saturn. And then when we blow up, you see Earth, and the moon. So for me, that gives us a perspective of our place just in our solar system. On that little dot, all of you are living on that little dot. The people you like, the people you don't like, all of them are living on that little dot that you see in there. So really, that gives you perspective. Even we think we are a big place, how small is our planet compared, to just our solar system. So you could imagine when you think about the rest, of the universe. And that's what we are going to be doing. So we are going to be bringing the spacecraft closer and closer and then actually flying it between the top of Saturn and the rings of Saturn. And who knows what we'll be discovering when that will happen. And that's what you will be seeing. If you are sitting on that, spacecraft, let's see, I think maybe I need to click twice. Yeah, so that's what actually will happen. If you are sitting on that spacecraft, that's what you'll be seeing. So we'll be coming really at the top of that atmosphere, and after a few loops, then we actually will crash in Saturn. Now, I'm sure somebody is going to ask the question, why are you crashing it, on Saturn? And as I told you, because we are running out of fuel after 13 years, we want to avoid that the spacecraft will crash on one of the satellites of Saturn, because one of them is called Titan, which has oceans and rain, and it looks very much like Earth the way it used to be a few billion years ago, made of hydrocarbon. There is another satellite, which is called Enceladus, which have geysers shooting, so we think there is ocean. So we are concerned if we cannot control the spacecraft and it will crash on one of those satellites, it might pollute them with life coming from Earth. So we want to keep it fresh. So if in the future we go and land on those satellites, we'll make sure the spacecraft is clean so we don't take our own bugs, but we find what kind of life exists on those satellites. So that's why we are going to crash it into Saturn, and it's going to burn as it goes in that atmosphere. So keep watch on September 15, probably that will be in the front cover of many, many magazines. Now, the other place we spend a lot of time exploring is Mars, like Terry mentioned earlier. Now, the reason Mars gets attention, it's one of the closest planets to us. But more interesting, it has a lot of similarity with Earth. There are some differences, but it has a lot of similarity to it. Mars is about a quarter of size of Earth. So if you take the ocean away, the land surface on Mars and the land surface on Earth are about the same. So it's about a big place. Mars has polar caps. You see at the bottom, that white, that's polar caps made of H2O and carbon dioxide. So it's similar to our polar caps. The year on Mars is about 2 years on Earth, a little bit longer than that. And you see these polar caps expanding and shrinking, depending if it's winter or summer, on Mars. Mars has an atmosphere, thinner than our atmosphere, but it still has an atmosphere. When you look at the detail, it looks very similar to Earth. I mean, I'll tell you, guess which one is the Grand Canyon and which one is a canyon on Mars? Now, some of you, the people who are maybe a little bit geologists, would recognize the left one is the Grand Canyon in Arizona. The right one is the Grand Canyon on Mars. Looks very similar. We have volcanoes on Earth. There are volcanoes on Mars. The one to the right is Mount Olympus, which is the largest volcano in the solar system. That mountain is higher than the Himalayas, than Mount Everest. So clearly, when it formed in the past, there was a lot of geologic activity going on to form a mountain, like this. So clearly, Mars was a very active planet. Today, it's not active, but in the past, it was active. And if you look at the surface, guess which one is Mars and which one is Death Valley? Usually, I give this test to my students, and it's 50-50. Even I forget, which one is Mars and which one is. The only reason I know the one on the right is Earth. I'm not sure if you noticed at the beginning there was a little snake which was moving on it, so that's how I can tell that the right side picture is Earth and the left one is Mars. So the point I'm trying to make is when we send a human to Mars, the first astronaut who will land on Mars, she will think she's in Death Valley. It will look very much like Earth. And that's because the geology is very similar to the geology on our planet. Now, some of you might know that, but literally our country have had now for 13 years, we have had a rover continuously exploring Mars. Think about it. For 13 years, we had a rover, which is the one to the left, which is called Opportunity, actually driving and exploring that planet. And remember, we have to do that remotely. I wonder how many of you have a car which for the last 13 years, you haven't had to take it to the garage, to do some fixing on it. So this rover has been operating for 13 years. The one to the right, that's Curiosity, the one which we landed 4 years ago. That rover, effectively, on that rover, it's the size of your car. On that rover, you have the same equipment that you find in a major university chemistry lab. It has a small X-ray machine, to analyze the material that we take from Mars. We have an arm, we can drill, take samples, put them in an oven, heat that oven, see what gases come out of it. As I mentioned, we have an X-ray machine similar to what your doctor takes X-ray of your teeth, except a lot more expensive. That will tell us, what is made of, what is the material made of. We have what we call X-ray and gamma ray instrument, which tell us the detailed composition. We have a laser system which zaps a rock and see what gases get emitted from it. So to make a long story short, what we found out is that every element in your body, carbon, hydrogen, phosphorus, all what makes the DNA, actually exists on Mars. So the question now, the fundamental question, okay, if there was water on Mars in the past, if there is ice on it now, if it has the same geology, if it has the same fundamental elements, could have life evolved on that planet? And that's one of the things that we are trying to look at. We don't think we'll find present life, but most likely there was life in the past, and we want to find out how far it evolved. And if we find it, what is it based on? Is it based on the same DNA that we have here, or something very different than the DNA that form ourselves? And that's what the scene looks like. If you are a geologist, it immediately will look like a dry lake. Matter of fact, if you look closely when you drive to Mammoth and you see the Owens Valley lakes, the dry lakes, and they look very similar to it. You see this kind of layering, or the salt that is left when the lake evaporates, and you have salt left on the surface. So that was one of the indications that actually there were lakes, on Mars, and but it has dried up. And that's another picture of sand dunes. It looks very much like sand dunes you find in Arizona, so it's very similar, to what we have here. And the challenge, now one thing which is interesting to kind of give you a first-hand, now remember it takes about 20 minutes for a signal to get to Mars and about 20 minutes for the signal to come back. So we cannot joystick our rovers. They have to be smart enough that they can drive by themselves. I mean, we tell them in the morning, we would like you to do ABC, and the rover is smart enough to drive, and if there is hazard, to move away from the hazard, or if they get on a slope of a sand dune and the wheels start slipping, we don't want them to get stuck. The rover is smart enough that will stop and back off and say, no, I shouldn't be doing this. So that led to a lot of artificial intelligence that we had to develop, for these rovers. And now to what we are going to be doing next in that case is we are in the process of building a rover now. So if Terry brings a group, I would say about 2 years from now, you'll actually will see in our chamber us assembling, a new rover. But the purpose of this rover is somewhat different than the Curiosity we sent there. What this rover will do, it will drive around, look at interesting rock, drill in them, take samples, put them in little canister, and take about 30 to 40 samples and put them in one location. So later we can land, send a rover to those samples, grab them, put them in the nose of a rocket that we land with us, launch that rocket in orbit, put the sample in orbit around Mars. We send a spacecraft to rendezvous with them and bring those samples back, to Earth. Piece of cake. We can do that. So that's going to be one of the biggest challenges that our nation will be doing, at JPL in the next decade, in the decade of 20s. And that's what some of the young people here will be actually working on. Now, to make it a little bit more dramatic, but there is a scientific reason for it, we're also going to have a little helicopter, so a little drone which will be going with that rover, and then we'll go and fly in front of the rover, survey the area, and tell the rover where there are interesting places, to go. So that, it looks like, gee, there are lots of drones that we do here. What's so special? Why is JPL doing that? Well, the challenge is the atmosphere of Mars is only 1% the pressure of the atmosphere on Earth. So this drone will be like you are flying at 100,000 feet altitude, where there is very little air. And the challenge is, how do we build a whole helicopter with all the instrument and everything, and it all weighs less than a pound? So with the cameras, the communication, the intelligence of making it figure out where to land without tipping, and all of this thing has to be done in a little bit bigger than the glass which is sitting in front of you. So there's a lot of technologies that we have to develop, to make that happen. And the thing we are going to be doing particularly exciting in the future is, I'm sure you all hear about virtual reality and, all these glasses you put on. So what we are going to be doing with this mission, and we have worked with Microsoft to develop these glasses, is that you put the glasses on, the data comes down, and it will transpose you as if you are next to the rover on Mars. The way we do scientific planning now, we have hundreds of scientists around the world, sitting down on their computer, going on WebEx, trying to debate what to do, and then decide what we are going to do, send it to the rover. At that time, any one of you can get one of these glasses. You sit at home, and you'll be as if you are in the mission operation room at JPL. We transpose you to Mars, and you'll be walking next to that rover on Mars, and you'll say, wow, this is an interesting rock. Maybe we should take a sample of it and automatically get translated into commands, and we can send it to the rover to actually drill in that rock. So basically, all of you could be, in principle, participant in our exploration in real time, not by doing some fake animation or something. It's actual data. And matter of fact, if you visit JPL now, we actually demonstrated doing some of that with some delay. We're not yet fully at that stage. So that's one of the advances that we'll be doing. And all of this will lead, I would say, 20 years from now for possibly sending a human to Mars. I was talking with students earlier today. I assume many of you have seen the movie The Martian, and I hope you enjoyed it. What I like about that movie, other than JPL is highlighted all over the place, I'm not sure I like the director of JPL in that room. The real director is better looking than the director in that movie. But what's interesting about it is that within 20 years from now, all of that could happen. What you saw in that movie could happen in the next 20 years. It's not as crazy as it seems. It's not as science fiction. There is a little bit of Hollywood and a little of drama, but all of that is within our reach in the next 20 years to be able to do what you saw in that movie. The other really exciting place, particularly with the topic of looking for life, is Europa. Europa is a satellite of Jupiter. It's roughly, you can think of it, about a little bit bigger than our moon. It's all made of ice. We know that from a mission that John Cassini was in charge of, called Galileo. It's made of ice on the surface. It has organic material. And you see these big cracks that you see in that picture. And when you zoom on them and look at the detail, it looks very similar to when you fly to Europe over the North Pole. See this ice floating, on the ocean? So we believe that there is an ocean just below that ice. And a liquid ocean of H2O, which means the temperature is like the temperature here, if it's liquid water that is in it. So a key question is, could there be life today? Because you have the basic ingredient, you have the water, You have the heat, which melts that ice. You have the organic material. So could have life exist today in that? And what we want to do, we're starting on a mission, and that's what at least our model, you see this ice floating at the top, looks very much like the ice you see over the Arctic. And we believe that the ocean below that ice has more water than our whole planet has water, be it in the oceans and the rivers, that we have here. So what we are planning now to do is to do 2 missions in the near term, one which will have a spacecraft in orbit around Jupiter, which flies a series of flyby of Europa and take detailed picture, detailed analysis, but particularly have a radar on it, which will sound the ice to determine how thick that ice is, and where possibly the ice might be thin. Then we'll be putting a lander, which will land on the surface, look at the detail of the ice, how hard it is, what is it made of. And ultimately, what we want to do is to put a lander which will melt its way in that ice and get a submarine in that ocean. And this is an example of a submarine that we are testing now in the Arctic, where we drilled a hole, we put that submarine below the surface, and it's driving upside down. It's like a rover. It floats up, hits the ice, and drive upside down on that ice, which will allow a similar kind of system will allow us to do the same thing on the Europa in the future. So now let me bring you to our own planet and give you some flavor of some of the things we are doing on our own planet. I mean, we have 4 big questions that we are looking at related to our environment. Number 1 is we know now that the ocean is rising, and I'll show you some data from it. The question is it going to continue to rise because of the change in our climate? And if it continues to rise, guess what happens if you have property in Florida in a very flat area? That will not do very well for real estate in that area. Do we have enough water? Now, yeah, we had a lot of water in the last couple of weeks, but across the world, there is a major issue about water availability for irrigation and continuing life. And how do you manage, that water? Are we prepared for an extreme event, an earthquake happening, eruption? Can we predict those things? Can we develop the capability to predict when an earthquake will happen in Los Angeles so we are prepared, for it? And the last one is about the carbon, which is included in our biodiversity. So these are 4 big questions that we are working on. And let me give you one flavor for each one of them. There is no question the ocean is rising. You look at the bottom right, this is measurement we have been taken for the last 40 years, or last 20 years, and the ocean continuously is rising. And part of it is coming from 2 reasons. One of it is the increase in temperature that expands the water, and also the melting of the ice in the Arctic and the Antarctica, and that brings water in the ocean, and the ocean continues to rise. If we continue on that rate, within the next 50 years, most of the coastal region in the US will be completely flooded. And literally, there are trillions and trillions of economic activity happening along the coast, real estate and all kinds. So that's one major issue we need to at least know how to handle. The melting in the polar ice. We have a mission which actually continuously measure how much ice there is in Greenland. And you look at the top right, and you can clearly see that the amount of ice in Greenland is decreasing because of the change in temperature and the increase in time. You don't need very much increase. A fraction of a degree can melt a lot of ice in Greenland, and all that ice comes into the ocean. Looking at the water table, what you see on the left is California in 2002, and that color is the amount of water which is in the water table in the Central Valley. On the right, we have lost, as you can see in the bottom, closely to 30 to 40 centimeters of water have gone out of that water table because we haven't had enough snow in the Sierras over 2 decades, and basically, the farmers are pumping out all that water, and we are losing that water. And we can measure that from satellite by measuring the gravity field, of the Earth. So hopefully this kind of information, as we get a long-term record, it will help us how to manage it better. It's not going to create water. I mean, we cannot create water at JPL. We can walk on water, but we cannot create water. But it allows us to manage things in a better way, than what we are doing now. Earthquake. That picture on the left is literally a picture of the Napa Valley earthquake. when you see you move from one blue color to another blue color, that tell you the surface have moved few centimeters. So we can literally take a picture of where the displacement actually occurred across all of California, and that will allow us to guide the rescue teams because they will tell them where the most damage actually occurred almost instantaneously, from satellites. Now, what ultimately we want to do is to see, can we map the stress along a fault, as it bends the crust of the Earth, so we can tell which area are high risk of actually an earthquake happen. If you see a lot of displacement, and you take a picture of it, you can say this area is high risk, this area is low risk. So that's something which will be in our reach within the next 5 to 10 years. That we're working all, and literally not only in California, map the whole world, and do that on a daily basis. We'll be seeing what motion is occurring down to fraction of a centimeter. And just to give you one other example of some of the applications, this is a mission that I was a principal investigator on. For literally 4,000 years, people developed technique of how to do topography, doing these contour maps. I'm sure you use some of these contour maps when you go hiking. Scientists use them to look at mountains, doing 3D pictures. And then literally in 11 days on one mission, we were able to map the whole world and generate data like this. So this data you see of Los Angeles, it came out from one of the space missions. You can visualize 3D, the environment you have in, you can zoom on it, and that's available to everybody. And this was done in 11 days on one of the shuttle missions and replaced an art which was developed over basically 400 years, with thousands of people have to work on it. So that gives you a little flavor of some of the benefit that these things will do. And finally, the last example I want to touch on, a couple of charts, is about looking at other planets that we are finding now in the sky. Just imagine, this is a fake, New York Times. Just imagine the first time we find a planet which looks like our planet, which have oceans on it, which have the temperatures that we have here, and any indication that there might be life on it. I mean, that will change our concept of our place in this universe. And it sure will make the front news on New York Times, and I'm sure the president will tweet about it immediately the following day. But this is not inconceivable. So let me show you how we actually do detect planet today. We have a mission called Kepler that basically was launched a few years ago, and we literally found thousands of planets. Now, the way we do it, because planets, the stars are very far away. We look at the star, measure the brightness, and if there is a planet around it, when it comes in front of the star, it blocks a little bit of the light. So you see a little dip, which happens. And if you see that dip repeating again and repeating again, that tells you there is something which is orbiting that star. And if you measure the periodicity, how long is it between two dips, that tells me what's the period of the star. If you measure how deep is the dip, that tells you how big the planet is, because a bigger planet will block more of the star than a small planet. So by using that technique, we actually have literally found thousands of planets around neighboring stars around us. So now the next step, what we want to do is actually start taking images, of those planets. And we'll use the same technique I mentioned earlier when I show you Saturn. Again, when I look at those lights, which is the star in there, it's very bright and we cannot see things around it. And if I block the light, now all of a sudden I can see all of you. That's what we are going to do on a future telescope. We are going to launch a telescope, and in the focal plane of the telescope, we are going to put a little teeny dot, and we are going to line it up with a star so we can block the light from the star and be able to see the planets which are around it and take pictures of it. And in technical terms, we call it a coronagraph, that thing. So that's the kind of technique we're going to be using in the next decade. And if you invite me 10 years from now to come and talk, I'll show you basically what I call the family portrait of the neighboring few hundred, planetary system around us. So finally, in closing, we had some of our artists at JPL. You can go on our website and print those posters from it, where we ask them, sit down. We have 6 artists who work at JPL, and their job is to communicate to the public in an artistic way, what we do at JPL. And this is their imagination. What would life be on those planets if we detect them? And just let me give you one example. The one to the right, Turned out it's a planet called Kepler-16b that was discovered, and it's around a double star. That means there are 2 stars there. So if you live on it, you will see 2 suns, which are in there. So you have a double shadow on the ground. So that's what we were trying. The one on the complete left, it turned out it's a planet around what we call a cold star. That means it emits most of its energy, not in the visible, but in the infrared, which is a red color. So in there, we think grass will not be green, it will be red. So the guys are saying, you see, so things are, the grass is red on the other side of the fence instead of the grass is green on the other side. So that's one way of communicating to the public. So that's in a summary what we do, and we dare mighty things at JPL and at Caltech, and that's what we have done in the last 15 years.
Charles, thank you so much for daring mighty things for so long. We have a microphone in the audience. Alexander is carrying it, so if you have a question, please put your hand up. Alexander, you have someone to ask a question? Go ahead.
What is the most promising technology that will enable a spacecraft to achieve interstellar travel or approach the speed of light?
Okay, make sure. So you are talking about technology for interstellar travel?
Yeah.
Okay. Unfortunately, or unfortunately, depending how you look at it, the universe is very big. So the nearest star to us is about 4 light years. It's called Alpha Centauri. That means at the speed of light, it will take you 4 years to get there. So when you look at Alpha Centauri and you look at the light coming from it, that's not what's being emitted now. It was emitted 4 years ago. Now, to the best of our ability, today's technology, it will take us close to 50 to 60,000 years to get to Alpha Centauri. So we need to develop technique which can get spacecraft to move much, much faster than we have now. And there are a number of ideas. All of them require a couple of dozen miracles, but But again, when the Wright brothers did their first flight, who would have thought in 100 years would be just going to LAX, hop on a plane, and travel to Washington or something. So these miracles could happen. So sometimes people are talking about having laser beams, which will kind of use laser light to push those spacecraft. Or some people are thinking about matter, antimatter, which will have a lot of energy, that you can mix them together and generate higher speed. So it requires a smart person like you to really come with some inventions so we can get our speed at, let's say, to about 1/10 or even 1/100 of the speed of light. And that will allow you to get there in 100 years, 150 years, which is not bad. Usually I tell people that will be a great legacy for our great grandkids, is we launch a spacecraft which will get there, when they are adults. And a perfect example I would think about is when people start cathedrals in Europe in the Middle Age. They knew it's going to take a couple of 100 years to build those cathedrals, but they still went ahead and built them, and then the following generations, kind of benefited from it. So if you can figure out a way to get to about even 1% or maybe 2% of the speed of light, then it will make interstellar exploration, possible.
In this time of rising debt and political tension and incompetence, how can you get Congress to fund your missions?
Okay, you should have come to the meeting with the students earlier because I got asked that question, also. Well, the key thing is at the end you have to explain to Congress why is this important. Why is it important for our nation to undertake, this kind of exploration? I mean, clearly, and there are different way of communicating, to a congressman. It's always a challenge for a scientist to explain to non-scientists why it is important. So first there is the scientific intellectual argument, that we gave. The other one is the inspirational argument. I don't know how old you are, but I grew up during the Apollo program. And that was a big inspiration in the United States. The ability of our country to do great things. And it led to a lot of people wanting to study engineering and science. They didn't end going into space, but they ended doing all kinds of other things, because of their engineering talent. And that I think is something which is very, very important to our nation, is to have inspirational thing which get people to feel that our country can do great things. Like you see here, at a minute amount of cost, on doing that. Usually people ask me, well, how much did that rover cost? The Curiosity. I tell them, well, that costed one movie ticket per American citizen in a decade. That's how much that rover costed. I don't tell them it's 2 billion, but if you do the math, it's 2. But it hits people, saying, wow, just for the cost of a movie ticket, look what inspiration we get for our young kids from doing that. And in general, we get pretty good support from Congress, irrelevant if they are Republican or Democrat. They do different emphasis a little bit. In general, the Democrats tend to favor Earth observation, climate change, and so on, and they still support, planetary. Republicans tend to support more planetary. So when I was director at JPL, part of my job is to go at least once a month to go to the Hill and meet with the appropriate congressmen and show them what we do, get them excited, to do that. And in general, it was pretty successful.
Can you speak about the OSIRIS-REx?
Let's see,
right
I can
here,
see.
back here.
Oh, sorry.
Can you speak about the OSIRIS-REx? That just
OSIRIS-REx,
launched up,
okay.
OSIRIS-REx.
Yeah, no, she's referring to a mission which was launched, I think, about a year ago. And it's a spacecraft which is heading toward an asteroid. And it's going to come very close to the asteroid, almost literally land on it, shoot a kind of like a harpoon, pull a sample from that asteroid and actually bring it back to Earth. I mean, even that we can develop very sophisticated instrument, still you cannot replace, all the equipment that we have here on Earth. Plus, with all the advances happening, when we bring samples, like what we did from the moon, you don't sit down and analyze all of them at the same time. You take a small piece of it, you analyze it today, other piece you conserve it for 5 years from now when there is a more capable instrument. 10 years from now, there'll be even more capable instruments to do that. And what we want to understand is what are asteroids made of? And are they part of a planet which blew up in pieces? Or were they left over from the formation of the solar system where they didn't get together and form actually a planet? So these are some of the things. So that will be, I think the sample is coming back in about 3 years from now. And we're very good at coming with very fancy name like OSIRIS-REx or something like that. It stands for something. I don't remember what it is now.
Thank you for your talk. I happened to be yesterday at NASA Ames Research Center in Mountain View, and I was told that there are multiple gigatons of water on the surface of the moon in the polar regions, and I'm wondering if you have an opinion about whether we should take a manned mission back to the moon prior to a mission to Mars as a sort of test case.
Yeah, right on. This is always a continuing debate which is going, if should we send a human, next step, should we send a human to the moon or should we send them to Mars? Yes, there is some belief that there is ice, at the North Pole of the moon in area where the sun never shines on them, like in the shadow and the way the orbit of the moon is. There are some areas where, and people speculate, we don't have an actual proof, but they speculate that actually ice would condense and stay in there. Personally, I can tell you my personal opinion. I personally think we've been there, we have done that, on the moon. Scientifically, it's interesting, but the moon is a very arid place. You'll never be able to expect, to be able to live on it or to find indication of past life, on it. On the other hand, it's close by. Take you 3 days, to get there. On the other hand, Mars, even that it's much more challenging, to do that, there is possibility of terraforming on Mars. We know there is ice. We know we can pull water, from that ice. So there is always a debate, and depending on your perspective. I personally think that for the young generation, and I ask usually people at JPL, tell them, would you rather go send a human to the moon or to Mars? And the normal reaction I get, the moon, that's what our grandparents did. And there is a point to it. Because again, the human missions, and I'm very supportive of the human mission coming from a robotic center. But we can do all the science with robots. For the cost of a human mission, we can send 500 rovers, to go to Mars, which can explore the whole planet. However, there is a big piece of inspiration which comes with a human. When you are sending astronaut or your neighbor or somebody you know or somebody. So it has to be something, what I call something grand and inspirational. I don't know. Personally, I don't think the moon will play that role, but I might be wrong also.
You showed that really exciting mission that's going to go to
Sorry,
Europa.
can you raise your hand?
Hi.
Oh, there.
You showed that really exciting mission that's going to Europa. I think it's called Bruley.
Wait, can you speak a little louder?
My question to you is, that mission that's going to Europa, I know that there's a department at NASA, it's called the Department of Planetary Protection, and it protects against cross-contamination between the Earth and whatever planet we're visiting. So my question is, how will you protect, when you go and visit planets that have water, from bacteria from the Earth so that we don't go and discover ourselves?
Yeah. So you're talking about possibly contaminating some of these places? Is that what you're... No, and that is a serious issue, and there are international agreement on how do we actually clean spacecraft, and there is a protocol of how we do that. So if we are putting a spacecraft in orbit, usually we don't have to go through that process. That's like the case of Cassini. But on the other hand, if we are landing or if we are putting a submarine and so on, we have to go through a very rigorous process of cleaning those spacecraft, and it ranges from chemical cleaning to actually baking those spacecraft for many, many days, and which makes them much more challenging to develop because you have to convince other people and yourself that you are basically, you might not be perfect, but at least we'll do everything we can. So the rovers that we send to Mars, actually we go through a lot of what called planetary protection kind of activity, and it's always a challenge because the engineers, they just want to build the darn thing and launch it, and you have the biologists which want to make sure it's absolutely clean, from doing that. So it is a challenge, on doing that. But we have a protocol to do it. Because, one of the things, I know that my friend Elon Musk came and talked here, and he wants to send spacecraft, land them on Mars, and so on. But he hasn't faced yet what would it take to do the planetary protection, on doing that. So that's going to be a huge hurdle. How do you take these big capsules, particularly if you have humans in them, and make sure you are not taking all our bugs and all the things we have here to another planet. For exploration, it might be fine, but for science purpose, if we're trying to find life on Mars and what is it made of, you want to make sure you are just not taking your bugs, with you.
Let's take two more.
Yeah, the question is about commercial, versus, I assume commercial versus what the government does. Is that correct, what you're asking? Yeah. The way we look at it, we love to have the commercial sector get more involved. And the way we look at it, that the role of the government, like when you do in any exploration, is to open new frontiers and things that the private sector is not willing to put the kind of money that is required to develop, because it's very risky to do these things and require a fair amount of investment. But once we develop that technology, we want to turn it over to the private sector and have them make a business out of it. And let me give you a couple of examples. Again, I keep mentioning SpaceX because I've had a lot of admiration for them. SpaceX hasn't invited a darn thing in technology. They are basically using the technologies that NASA developed for the last 40 years. Where they are smart, or Elon got a lot of, is they are much more efficient in using it. The government is not very good of being efficient to do things. Private sector, they want to make profit at the end, so they are very efficient to do that. So that's the role that the government plays. You open new frontier, you do new things, you develop new technology. Then we want to turn them over to the private sector to make a big business for our country from them. And let me give you a couple of other examples. I'm sure you have a cell phone. Even that you are 10 or something, I'm sure your parents got you a cell phone. People don't realize that the code on that cell phone, which communicate with the towers, was actually developed at JPL for communicating with our deep spacecraft, with deep space spacecraft about 40 years ago. An entrepreneur picked it up and said, gee, I can make something of it. The camera, the one that you take selfies and you send to your mom, about it. That camera actually was developed also at JPL, the focal plane, for our telescopes. because they didn't exist in the past. We call them CCDs. They didn't exist, so we invested literally a lot of money into developing these for our telescope. And then an entrepreneur thought, gee, I can take this thing and use it in a camera. So that's an example of where I see the commercial and the government does that. So we love to see the commercial sector taking things, particularly in Earth's orbit, because the technology is pretty well available. And we focus on the deep space where we have to develop new kind, of technology.
I'm thinking back to your last slide with the newspaper. How can you tell what would count as something being alive so that you could have that news? I'm thinking many times it might be easy if they look like us or something that exists here. But that, of course, is a very anthropocentric or Earth-centric hope. What if the life just looks so extremely different that it would be hard for us to count it or to say, okay, here it is, we found it.
I have a person who lives in my house which asks me that question all the time. And that's my wife here. And she keeps telling me, Charles, be open-minded. Life might be different than the life I've had. And you are right. We tend to look at life which look like us because we are familiar, with it on the DNA. So the question is a very good question, is how do you keep an open mind and look at things which could be life, which reproduce, depending what your definition, of life. But it could be based on something completely different. It could be based on silicon instead of carbon. I was just reading on BBC that something, where, the DNA is based on 4 elements. They were able to come with 2 additional elements and develop a DNA which consists of 6 elements instead of 4 basic elements. So that's a very different life than what we have. I mean, it's in the lab and so on. So yeah, we have to keep an open mind, and that is a challenge. Now, the other question you might ask is when we see another planet, how can we tell there is life on it? And one of the ways which get you a little bit there is by looking at what's the chemical composition on that planet. Now, it's a little dot. We can take the light and we do what we call spectroscopy, which allow us to analyze the composition. So if you find that that planet has a temperature where water is liquid, that's getting interesting. If you find oxygen, that's getting a little bit more interesting. If you find methane, that's getting even more interesting because that's an organic material. If you find chlorofluorocarbons, the one which get emitted from your refrigerator, now that's getting really interesting because that molecule does not exist in the world by itself. It's generated by industrial activity. So there are a few tricks you can use where you can tell, is that material amenable for life? Could it be generated not normally in nature, but somebody has to generate it, in a chemical process, and that could indicate of some industrial, kind of activity. So your question is very, very right on, and it's a challenge to figure out how do we do that.
And we'll be working on that question for quite some time to come.
Okay.
Dr. Elachi, thank you so much for raising our gaze to the planet.